Our next speaker is from Haifa, which is a bit closer to Beersheba than Maryland. His name is Professor Assaf Schuster. Please.
Thank you for inviting me to speak here. It's pretty impressive what you can do in Beersheba in regards of conferences. But I don't know who thinks that Haifa is closer to Beersheba than Maryland. It's really not the case. But anyway, so today I will talk about lightweight monitoring of distributed data streams. It's a joint work with my co-author Danny Keren and a student Arnon Laserson. Of course, they did all the work. I get to do the speeches. And it's a paper that is about to appear in KDD later this year. So what is monitoring all about? It's about distributed stream networks and monitoring them. We find them, what are distributed stream networks? They are large-scale and widespread network systems. They continuously produce data in a distributed fashion. So there are nodes that are distributed geographically, and they continuously produce data, like think of sensor networks, for instance, in high volume and dynamic nature. And somehow we want to monitor all the data that is produced by all the nodes in order to detect some global condition. When this global condition, we want to make sure we realize that it happens and to alert in real time. And we find distributed streaming networks that we want to monitor in many, many different areas, such as financial data analysis, traffic networks, and sensor networks, and so on and so forth, disaster monitoring, and so on. All right, so let me talk about an example. So in Haifa, we have high pollution, air pollution, as you well known. So the mayor is trying to do something about it. So what does he do? He distributes many sensors around the city. And these sensors are not wired connected, they are wireless connected. And they monitor the concentration of different pollutants in the air, like nitrogen dioxide, monoxide, carbon monoxide and dioxide, sulfur monoxide and ozone, and so on and so forth. And the vector of the concentrations is different in different locations. This is why it's distributed. In the center of the city, the concentration is much higher than on the beach, for instance. And so, but according to the law, the mayor needs to monitor the average of all the readings, the average of the beach, the average of the center of the city. And on that average, it applies a certain function, which is called air quality index. And the mayor needs to issue an alert immediately when the air quality index rises above a certain threshold, a well-known threshold, the global threshold. And while this alert is issued, the refineries and all the companies that produce all the pollution needs to do something about it, move to lower pollutant fuel, move to gas, and so on and so forth. Of course, it's a very good question why they did not work on lower pollutant fuel from the first place, but that's a different talk that I don't have time to get into. And you can talk about sensor networks. You find them everywhere today, monitoring fields, monitoring the air condition in this room, monitoring a lot of stuff. You can talk about search engines. There's a lot of monitoring on large infrastructures. For instance, why do you need to monitor those large infrastructures? Because even a small change in the operation of those large infrastructures, such as that of the cloud of Google, for instance, or Facebook, and so on, even a very small optimization of the operation of those big infrastructures was a hell lot of money. So you're monitoring them all the time, and based on the results, you optimize them all the time. Cloud health monitoring 1, cloud health monitoring 2. When the cloud goes down, everything goes down with it, together with the companies. And that's Amazon. I could talk about Microsoft's Azure or Facebook earlier this year, and Google, and so on. So monitoring over dynamic distributed streaming data, large data, huge data, is a big thing. And we started looking at it back in 2003. We were supported by many funding agencies, and this is the time to say thank you. And we have a list of publications trying to optimize monitoring. The model, and in a second I'll tell you what the challenges are, but before I do that, let's look at the model. The model is very simple. You have nodes. Each of the nodes has a vector of readings, like the vector of pollutants, concentrations, and all of them talk to a coordinator which coordinates everything. And once the average of the reading, taking a function above that average, is greater than some threshold, you need to alert. That's all. It's a very simple model, and despite its simplicity, it captures an amazing amount of situations in life. Again, it's a set of nodes distributed usually geographically, and they talk to a single coordinator, and that coordinator needs to issue an alert whenever some function, which is our application, and I talk which are the applications that we deal with, that some function over the average of the reading is greater than a threshold. Once it crosses the threshold, we need to issue an alert in real time. Okay, that's the model. And, sorry. What are the challenges? So let's try naive monitoring. Naive monitoring, every node, whenever there's a new data item on a new data vector, it simply sends it to the coordinator. And the coordinator maintains a global state at any point in time. And whenever the function over the global state from the readings of all the nodes crosses a threshold, it issues an alert. What is the problem with that? Sometimes the number of nodes is thousands, hundreds of thousands, and even millions. You want to monitor a global infrastructure like Microsoft's Azure, you have millions of agents, each reporting, and if you want them to report of all the data that they collect, forget it. It's too much data. It's too much resources that you need as a central location, as a coordinator location. It's too much bandwidth that you need them to send. It's too much energy. If those nodes, God forbids, are energized by battery, forget it. It's too much to send. Sending data is usually believed to take half of the energy that is consumed by big data centers, and it's just too much. Okay, so this CAM, the naive monitoring, is not being, as far as I know, is very rarely being executed. It's being implemented. Usually, people do some less naive monitoring. What is less naive monitoring? We do not notify the coordinator every time we have a new vector or new data coming in. We notify the coordinator every certain period of time, like every minute, or every second, or every hour, or every day, and so on. What is the problem with that? Periodical update of the coordinator leads us to a vicious trade-off. What is that trade-off? If the period is very small, the amount of communication is very high, because the nodes will transmit all the time to the coordinator. If the period is very large, then the real time becomes offline. Okay, what does it mean? The coordinator does not get the data in order to alert in real time. Like if the period is an hour, then the average amount of time that the coordinator will be notified about a change in the data is half an hour, and the worst case is an hour, and so the model is broken. So the coordinator will require, on average, half an hour to notify on something that should have been notified the second that it happened. Okay, so there's a problem. We are in a trade-off. How do we deal with this trade-off? We are going to minimize communication. And in 2006, sorry, this should be 2006 over there, we suggested the way to do that. We call this geometric monitoring, or GM. We want to communicate only if the global condition is broken. What do? We take the global condition, we break it into local conditions, and we let each and every one of the nodes follow its local condition. Now, not all the local conditions should be the same, but let's think about it, because we only have 5 minutes, as if they are the same. So the key is to decompose the global conditions into efficient local conditions, so that once the local condition is broken, the node where the local condition was broken will talk to the coordinator. The coordinator will talk to everybody and make sure that this was a false alarm. Or, on the other hand, it may be a true alarm, so it will issue an alert immediately. All right? So the key is to compile good local conditions. The GM, with GM, we were able to get amazingly good results on reducing the amount of communication by orders of magnitude, really, many orders of magnitude. We were able to build systems that transmitted to the coordinator only when there was a risk that the global condition was breached. The problem was that when we started to test geometric monitoring on wireless systems, on Internet of Things like environment, on thin devices that have low amount of resources, on systems where communication was over cellular or wireless network connections and so on. The amount of computation by the end nodes was very, very high. Okay, so we had to find something else. Those nodes were becoming thin, were becoming not higher. The amount of CPU and memory that we had in order to do the monitoring in geometric monitoring was not as good. So, so this leads us to the current paper that is going to appear in KDD, in which we were able to simplify the whole thing, reduce the amount of communication computation by orders of magnitude, and still even reduce the amount of communication from geometric monitoring. And how do we do that? So I'll only give you the very high level from 20,000 feet high. It all begins with the observation that monitoring in a distributed system, when the monitored function in convex, is trivial. Okay? Why? So consider a system that is composed of two nodes, V1 and V2. And these are the values that I have. The average is here. And the average will always, since the function is convex, is always be lower than the values at the endpoints. And thus, it is trivial to compile local conditions from the global condition, because we want to make sure that the average does not cross the threshold. We simply make sure at each and every point that the point locally does not cross the threshold. Okay? So it's very easy to monitor convex function. On the other hand, it's very hard to monitor a non-convex function, in this case a concave function, because the value of f on the average can reach above the threshold without the endpoints knowing it. Okay, so if one of the local conditions is breached, it may be a true violation of the global condition, in which case the coordinator needs to alert, and it may be a false breach of the global condition. It's only a local condition, but breach. In any case, the coordinator can check it very easily and make sure that there's no false alarms. If there's a need for synchronization, if it's a false alarm, then the coordinator just compute the average of everybody, inform everybody about the new average, and from now on they only start looking at the drifts from that global average. And since everything is linear, the average of the drifts is the average of the true values, and everything is great. All right, so one more minute. Now you're saying, okay, so you know how to monitor a convex function. How do you monitor a non-convex function? And the answer is you just put a convex function above it, and you make sure to control the gaps that are left here. I don't have time to tell you how, but these gaps are monitored, and everything is great. And we also have a way to compute this convex function that approximates, in a way, the non-convex function, and you have to read the paper if you're interested about that. Let me just go over the results. By the way, this is the way you put the convex cover. Here you put it below because the threshold is below, so it's convex on the reverse way. This is the Pearson correlation coefficient that we just heard about from in the previous talk. And this is the global value at this point. And this is a convex cover. The blue manifold is just a convex cover below the Pearson correlation. And you can see that it sticks to it at the current global value, and it just gets away from it. So the Pearson correlation coefficient is a saddle. Okay, it's not convex. But you can see that the convex is really approximating the Pearson correlation coefficient. And so in the evaluation, let's immediately go to the evaluation where we tried it on mini PC, on an Edison Internet of Things like CPU from Intel. And you can see that the difference in the amount of computations that you need in geometric monitoring, which was the previous state of the art, to the new method, which we call CB, it can reach 1 or 2 or 3 or 4 or 5 or 6 orders of magnitude. And this is on a kernel of Pearson correlation coefficient. And also the communication is reduced. Just to summarize, it's a new method for monitoring threshold function over distributed streams. The runtime is low by orders of magnitude. The communication is reduced as well. And we have a lot of future work, of course. And that's it.
Okay, thank you very much. Okay, it's just a question from me. Mm-hmm. What actually happens if your function is concave and not convex? Because some of the functions may be.
And you're talking about a function which is concave and the threshold is above it?
Yeah, just the opposite.
So in this, for this situation, we have a previous paper that appeared in VLDB 2015 where we show that the best safe zone, so we call these local conditions that we compile to the different nodes the safe zone. And the base safe zone is just a straight line that is perpendicular to the concave function precisely at the place where the global data resides. Okay, so I can draw it if I had time, but all right.
You have a solution. Thank you very much again.